to resonate out that
This
inductance.
meeting is being recorded.
At 70 megahertz. Cool. So where are we going to find a 2 picofarad capacitor in this mess? Well, let's go take a look at the split ground that they had. The split ground had a signal by the name of 5 VDC underscore ref underscore ground. It's the classic issue. They split the ground. It always gets you in trouble. In this particular instance, that ground was actually a trace on top of the board, and there was a shunt capacitance between those traces and those pads and the ground structure. So if you go in and you painstakingly measure that area of those traces and pads, that turns out to be something on the order of 12.7 micrometers squared. Kind of a small number, but it produced a capacitance of 2.1 picofarads. Okay, cool. So now let's check to see if that capacitance, where is it going to resonate? Well, it's going to resonate at 70.1 megahertz or thereabouts. And of course, that means we found the problem. We didn't use any test equipment. We didn't use a spectrum analyzer. We didn't probe anything. We just looked at things and measured the lengths of the wires. And off the screen, we measured the area of the conductors. And we said, yep, there's the problem. What you have, well, let me getting ahead of myself. What you have here is a capacitor built into the printed circuit board. And when that capacitor resonates with the inductance of the harness, all of a sudden you have those two grounds moving back and forth and preventing these two little circuits from working. So I ask myself, as a consultant and an educator, just why is it that people keep getting this ground issue so wrong? Over and over again, I see where people are splitting their grounds and it causes havoc. Well, I looked at the way the classic transmission line theory is taught in every university on the planet. And I find that they unintentionally sabotage the ability of the electrical engineers to understand EMC. They teach that ground is ideal. And as we all know, ground is not ideal and never was and never will be. Okay, so what do we do about that? Okay, well, I've been trying to communicate to people, particularly on LinkedIn, that ground is not ideal and that teaching transmission line theory with an ideal ground is both unnecessary and unproductive for the electrical engineers on the planet. If you take the classic schematic for transmission line theory, you can transform it into a schematic that actually makes sense. And then if you think about the center of this structure, you end up with a virtual ground between the two halves. And that virtual ground is ideal. And it will support the analysis that has been done in the past. So I'm on this jihad to try to explain to people that ground is not ideal, and it never will be ideal, and it never was ideal. So that's struggle number one. Struggle number two. Here we have a switch matrix. It was in a truck, a new truck. I won't say which OEM produced this truck, but there was a touchpad that was used for a cell phone embedded within the truck. And it had a problem. It detected RF at 220 megahertz. Okay, way cool. All right, you expose this module to 220 megahertz and the module thinks that a button has been depressed. Why is that? Why is it that when you irradiate this circuit, here I'm showing just a single row of the circuit, that this circuit thinks that a button has been depressed? Well, the answer to that question is simple. There's a resonating circuit that is absorbing RF energy at 220 megahertz. So if you would all take a look at this and you tell me, where is the 220 megahertz resonating circuit in this row of components? Well, I'll give you a hint. The hint is that the distance between the microprocessor and the switches is approximately 10 inches. And that's approximately 100 nanohenries. Now, if what you do is you say, okay, we got to get out there and back, so that you have 10 inches going out, you have 10 inches coming back, you have 20 inches. The total inductance of that loop can be estimated at 200 nanohenries. And here again, we ask ourselves, what capacitance do we need to resonate out that 200 nanohenries of inductance at 220 megahertz? Well, the answer to that is that you need a 2.6 picofarad capacitor to resonate out that inductance. So where are we going to find a 2.6 picofarad capacitor in this circuit? Anyone want to venture a guess? No? I'm going to give you a hint. If you change the value of this resistor down here, called resistor 105, if you increase the value of 105, the EMC performance gets worse. What does that tell us?
You got 1 minute left. 1 minute.
It tells you you have a parallel resonant circuit. So let's go ahead and take a look at what that means to us. It means that we're looking for a resonant circuit that will resonate at that frequency, that will absorb energy at that frequency. And we simply calculate the resonant frequency. Okay, so there we have to find out the capacitance of the diode. We go look at the data sheet, gives us the capacitance. We drop in a 0.5 picofarad for the open switch, 7 picofarads for the microprocessor, and 3.5 picofarads for the diodes. And sure enough, we get an answer of 230 megahertz. Boom. That's right there at 220 megahertz. We have found the problem. We didn't use a spectrum analyzer. We used a tape measure and our calculator. How do we fix it? Well, that's pretty easy. You add a resistor to lower the Q of the circuit. But where do you put the resistor? Well, you put the resistor at the input of the microprocessor. 100 ohms should do. And if you take my class, I'll give you actual equations for calculating what resistance you need to solve this problem.
Okay. Thank you, Joanna.
You're welcome.
I'm going to remove co-host. Okay. Next, we're going to move to Chris Semanson. Let's see if I can find Chris here. There he is.
Can I ask Joanna a question?
Can we hold the questions till afterwards, please? Till the end. We're tight time schedule. Sorry about that.
All right, I think Joanna's gonna have to stop sharing for me to start sharing.
Just a second. I'm going to make you the co-host now. See if this works.
Oh, it disappeared on me.
Okay, so try it now, Chris.
Sure. There we go. Screen. There we go. All right. Can everyone see this?
Yes.
Okay, great. Awesome. I won't be able to, hopefully I'll be able to get through this in about 5 minutes. It's more of an overview of an issue. I titled this one, When Spread Spectrum Goes Wrong, or How Not to Design Spread Spectrum for CISPR 25, or How to Educate Your Design Team of what spread spectrum is. So I'm Chris. I've come in and out of the IEEE EMC Society up in Michigan, and I'm a staff applications engineer at in Renesas. I'm a part of the automotive power group. We develop power management ICs, regulator and controllers. So we're on usually the source side of the problem and not the solving side of the problem. So our PMIX that we make, if some of you are aware of it, we have upwards of 1 to 3 modulators and 1 to 5 LDOs. So it's a really handy little piece of equipment to have, but it's also a very noisy little piece of equipment to have. So we implement a lot of tricks to distribute noise. One of these tricks, and so over here on this right, you see that we have a V in, we have a phase where we pulse the crap out of this little guy. This is with an integrated FET. You see we have a little inductor here, we have a capacitor, pretty much a standard switch regulator, or switching regulator. You see we sense our feedback here, and then we have that little thing that we'll call that the signal return path for the ground. So we offer tons of little tricks to distribute noise and to kind of mitigate the noise problem. We synchronize our, that should be FSW, our switching frequency being external source. So you can feed in PWM to kind of change this within limits. We offer slightly tunable switching frequencies. And then the one thing that everyone has heard about is we offer spread spectrum, that's a hard word to say, using various modulation techniques. I won't go into it. Some of them I understand, some of them I don't. I wrote an article about it in Compliance a little while back. But this story is about when spread spectrum goes wrong. So the problem that we had was a customer was turning on our spread spectrum during their CISPR 25 test. And they wanted to know why the conductive emissions they were measuring was not being reduced by any appreciable means. In fact, and our marketing person, a lovely individual, said it must be broken. So it turned out the device actually performed under the average limit, but over the peak limit. And they weren't getting any appreciable difference between when it was on or off. So after talking with people, it was interesting. The individuals down here are not quite like Detroit. So these guys aren't familiar with, these are designers. So they are really good at designing circuits, but when it comes to a system level thing, it's a little rough. So they weren't familiar with CISPR 25, and many, including the application engineer, not me, the other application engineer, how they didn't really understand how a spectrum analyzer worked on the inside. And so the bottom line was that it appeared to the customer that the spread spectrum was not functional. And it was kind of interesting to kind of dig in to see what happened and what we could do. And this was before a revision B tape out. So time was kind of critical, and we wanted to learn what we could do. So just a really quick overview. This is a really quick overview. Obviously, you have an input spectra from your switching frequency. It mixes with a local oscillator. And then you have these little fun little RBW settings. And I used to tell my students on how to switch these. You have these little resolution bandwidth guys. So we'll say this is low, this is medium, this is high. And then you have some envelope and video filtering. And then you have your display. So what was kind of interesting is I kind of was educating some of our design team on how this works is I can make these resolution bandwidth settings pretty selective or not selective at all. And that's going to depend upon, and that's going to impact the thing I see on the screen. So you can see in a low selectivity thing, I'm capturing both the fundamental and the first harmonic. You can kind of see on a second one, I'm capturing the fundamental and the first harmonic, but I'm starting to get a little bit of difference between the two lobes. And then you can kind of see on the third, I get individual lobes right here. And this isn't the most perfect. You would ideally see this main lobe maybe go down a little bit and maybe be up a little here, but you kind of get the idea that your selectivity on your resolution bandwidth depends upon the energy level that you see. So the two important things that were kind of missed here is, well, I'm sure they understood this, is here's what spread spectrum is doing. It jitters your PWM frequency and it spreads your fundamental frequencies out a little bit so that you no longer get these individual lines, you get these little jitters, and it's supposed to lower your frequency. And the one thing that everyone missed is CISPR 25, and I don't pretend to be an expert in this spec. I'm just kind of starting to keep learning it. It specifies a large amount of things, of which is the resolution bandwidth setting. So what's interesting is they compared this part, which was a new revision, which is the same process, to a previous part, and wanted to know why the previous part worked so much better. In fact, they even said that the new part's spread spectrum was much better. And I don't know what better means to some people, but they said it was better. So we sent this down to our EMC lab, I think in Palm Bay. It might have actually been up in Detroit, I can't really remember. So when the design and application engineers compared older products, which performed better, they noticed the spreading algorithm was different. And the newer product spreading fit inside the resolution bandwidth setting. So after looking at it, I have some pictures here in a second, but the newer product spreading fit quite right, almost perfectly inside the RBW settings for the CISPR 25. And this resulted in a reduction in average emission, but no impact or sometimes an increase in peak emissions. And so this is kind of what you got. And you're going to have to, I pulled this from another presentation, so I don't have a lot of hard numbers, but I think you can kind of see the idea. So this is the new product that we are giving issues. And so you see how it was spreading in these really tight individual groupings, the frequency spectra. And this is what they considered better. It was a much cleaner spread. So you got your 7 bands here. That's the older product. And I can't give you, unfortunately, I don't have relative amplitudes to show you, but you can kind of see the older project had a much sloppier clock and a much sloppier spreading situation. So there's some words down here, you know, this one spread it in a different way, 32 frequency bands versus the 7, and they're 1 nanosecond apart. The clock jitter was much looser, so the average energy bled into the neighboring bands more, and so it looked like it performed better, even though, well, I guess better is really a subjective word. So what they ended up doing, because I wanted to be quick on this, is they would end up taking this algorithm, and I should say algorithm, this circuit, and then applied it to this new product because they wanted to juke CISPR 25. So that is my story of how to educate and design, or educate individuals who don't necessarily know what they're designing for, or especially if it's late in the process. So thanks for your time.
Thank you, Chris. Thank you very much. Okay, our next presentation is solar panel manufacturing EMC with William Sommerville. Let me find you here.
Yeah, hi. You guys hear me okay?
Yeah, I've got to allow you to share. I'm going to make you a co-host now. You're now the co-host. Chris, I don't know if I can. Chris, I'm going to remove the co-host. Okay, anytime you're ready, Will.
All right, you guys see my screen here? Yeah?
Yes, we do.
Great. Okay, so I have 2 presentations. The first one here is actually a previous life of mine. I was working at a solar company, and so we're going to talk about some solar panel manufacturing. And at this solar company, it was a Michigan company called United Solar, and this was about 2010. We had a machine that was about a football field long, and it was depositing amorphous silicon on a thin film solar panel. And it's using a PECVD process, a plasma enhanced chemical vapor deposition process, which involves the plasma, which involves RF power to break apart some molecules in deposit. So we had 116 kilowatts of 13.56 megahertz RF power on this machine, as well as heat, because everything had to be at a particular temperature. We had a further 3/4 of a megawatt of heat that was a phase controlled heat system. And with the amorphous silicon is under a vacuum, and we're actually running a lot of hydrogen gas and other nasty gases that are used for semiconductor deposition, 300 liters a minute of hydrogen. And so a lot of big numbers here. And if you look forward, you can see some panels and some pictures here of the machine. We have a lot of RF power supplies, 13.56 megahertz power supplies going into some impedance matching networks to couple power into these plasmas. We have the center picture is the main 480 volt power distribution for the heater system. We have 4-aught gauge wires running through here. So if you know your 12 gauge wire and your 10 gauge wire, you go all the way down to 0 gauge, 00, 000, and 4-aught is quadruple 0 gauge, so very, very thick, like 1-inch thick cables routing all this heat around the machine. And then on the right hand, there are individual 70 volt circuits that are phase controlling the heat. And the way phase control works, you chop up a 60 hertz signal, and you have a lot of rises and falls there on your high current heat circuit. So there's tons of noise, both in the 13.56 megahertz spectrum, but also in kind of a lower band of frequency spectrum, just with these high current cutoffs here on the phase control heater circuits. I don't have a good spectrum data on that, but I think it looks a lot like what you just saw with the harmonics on the PWM in the last presentation. And so what we're doing, we're taking a silane gas system. It's SiH4. It's the gas. We put that into a plasma. It deposits silicon, and it also releases more hydrogen gas that we pump away. And a plasma is a nonlinear load. So if you're used to radio circuits and you understand, heterodyne receivers, whenever you have a nonlinear load on any, AC type of frequency, you get harmonics of that. So we get 2x and 3x of 13.56 megahertz. So lots and lots of noise, lots and lots of power. And all that gas gets pumped out in a separate room called the pump room. We have 4 giant industrial pumps here that are pumping out everything from these chambers, keeping a nice low vacuum pressure. But we have to look for leaks. We have to look for both nasty gases that are escaping, so this is the silane and other gases that are involved getting out into the atmosphere, which are poisonous. We want to make sure people aren't breathing those in. But on the other hand, we also want to make sure no oxygen from the atmosphere is getting into the machine, which is under vacuum pressure. So that oxygen, if it gets in there, could be an explosion hazard, but it also will ruin your solar panel. And so what we did is we have some oxygen sensors after the pumps, just before we burn off all the hydrogen. We have a burn box that's got a flame, and it burns all the hydrogen, all the nasty gases that are coming out of the system. And there's 3 oxygen sensors. They're redundant, so one sensor might fail, but we're going to have some redundancy to make sure that we're safe. And these oxygen sensors originally were lambda sensors, which are the same as what you might find in the exhaust system of a car, but there's some other technologies that we've used. The oxygen sensors that we were using have a current output, so anywhere from around 1/4 to 1/3 of a milliamp at atmospheric oxygen levels. But with our machine, we wanted to hard stop the machine, close every valve, shut down the machine if we had only a single microamp, which corresponds to 0.07% oxygen inside this 300 liters per minute of hydrogen gas pump. I know I'm covering a lot of ground here, but I think we can all agree you do not want oxygen in your hydrogen machine. And we put in several systems. The first 2 systems actually were pretty lucky. We had a little bit of interference, but you can imagine when you're looking for 1 microamp and you have about a megawatt of electrical power being consumed next door in the next room, it's very easy to pick up a microamp of current here. And so we had to up our shielding game. This is a story about shielding. So we have some nice metal cans that we put over our oxygen sensor. We have triple shielded cables. We have shorter cable runs, grounded everything as well as we can. We got bandwidth limited op amps that would not respond to the 13.56 and harmonics of radio frequency power that's running through the air. But I got to tell you though, after all that engineering, and we did engineer the heck out of this, we machined all this and precision fitted everything and bought special cables and everything. The thing that really saved the day, at the end of the day, after everything was, and I'm not proud of this, we wrapped everything in foil like a giant baked potato. So if you look at this entire area here in this bottom picture, all of that was completely covered in store-bought aluminum foil. We just caked it on several layers thick, and that is what saved our oxygen sensors from picking up all that radio frequency power and all the phase control heat, chopped up, magnetic energy that's coming out of the machine, and that's what kept the machine from hard stopping. So it's kind of a, I'm not trying to get into too much of the detail, but you can understand this is a pretty major shielding effort. We also did a lot of shielding on the machine side, adding beryllium copper, spring-loaded copper gaskets and things on all the components that were removable on the machine, and you know, used aluminum tape and other things to patch up anywhere where e-fields might be escaping from the machine. But that's all I have on this one, and I think in the interest of time we can move forward, but the story there.
Hey,
And by the way, I want to tell you, I'm enjoying everyone else's story. This is peak nerdism, and I love it, and I'm really happy to be part of this, even on St. Patrick's Day. It's great to see all the circuits and the schematics and the frequencies and all that.
fantastic. Well, thank you so much. We are recording this for those of you that missed the announcement earlier. So I did miss a little bit of Joanna at the beginning. I apologize for that, but it'll be available in a day or two. Okay, our next presentation is from Mike Hertz. Mike's presentation is on an EFT pulse mystery. So Mike, talk so I can find you here.
All right. Hi.
Oh,
Hi, everybody. Thanks for inviting us to do a roundtable discussion on different types of challenges. And I'll go ahead and share my screen here.
okay, great.
All right. So my topic's actually pretty similar to Chris's in terms of undersampling, aliasing type of topic. It was interesting to hear what Chris had to say. So the issue that I ran into was that typically when we're thinking of Nyquist sampling theorem, then we're looking at 2x oversampling over the highest frequency. And when it's a sine wave, then it's a simpler discussion because we might have an image like the one I put in the slide here. Can you hear me okay?
Yes, some people popped in, I need to mute. Sorry about that.
Oh, no problem. Okay, I thought maybe there's a question or you couldn't hear me. So in the image here, I've just got on the left-hand side is an example of undersampling where there's a faster sine wave, but the sample rate's too slow with these red dots. So it actually measures a sine wave that usually has the same shape, but it's got the wrong frequency characteristics. And so what would happen, for example, from undersampling is that you could have this faster sine wave on the left that's made up from the dashed lines, undersample it, and then an oscilloscope would show a slower alias signal. So what Nyquist sampling theorem says to do is to oversample by a factor of 2x. But what Nyquist was referring to is to oversample 2x relative to the highest analog frequency component. So in the case of a sine wave, it doesn't have harmonics. So what you're sampling is just the fundamental frequency. But in the case of signals that have more complex shape, then the sampling might need to be a lot higher. And so as one example I ran into is with EMC testing, which is the kind of stories we're talking about today. And what a EFT pulse looks like is it's got a very fast rise time, a slow fall time, typically rise times around 5 nanoseconds or so. And it comes in a burst, and then it's got a long gap, then another burst. But even within the burst, the EFT pulses have a very low duty cycle and a lot of gap between the different pulses. So this is an example here of an EFT tester. So I just took a picture where I'm holding the power cord. And normally a device that's being tested for EFT, you would hook it up to the power cord where it's including EFT into the power line itself. But before the EFT test is done, it first needs to get tested on an oscilloscope. And so you capture the EFT pulse coming out of the generator, make sure it meets all the requirements, and then do the EFT testing in the lab. So this is an example of capturing a EFT burst where we're looking at some of the leading pulses on it. And I set up the frequency measurement here. It's 10 kilohertz frequency, so that's a pretty low frequency. And I started out sampling it at 125 megasamples per second. And when we're thinking about Nyquist, if we were just looking at that fundamental frequency, then we could say, well, it's 10 kilohertz, and I'm sampled at 125 megasamples per second, so I'm oversampled at 12,500 times oversampling, so that should be overkill in most signals that one would capture. But here I could see some amplitude modulation. So this actually happened in the lab when I hooked it up, 125 megasamples per second. The EFT pulse is amplitude modulated along the top. And so I took a look at it and raised the sample rate up to 2.5 gigasamples per second. Now we're almost at 6 orders of magnitude oversampling. So it's about as high oversampling situation as one could run into. And here we're looking at, it's still a 10 kilohertz frequency, but it took getting up to around over a gigasample per second before that amplitudes of the EFT burst would level out. And as a comparison, I set the 125 megasamples side by side with 2.5 gigasamples, and we can see that it actually made a difference between being just over 5 orders of magnitude oversampling compared with 6 orders of magnitude oversampling on that fundamental frequency. Because the content of an EFT pulse is so high relative to its actual fundamental frequency. And taking a look at another one, I set up a comparison at 100 megasamples per second, so it'd be exactly 10,000 times oversampled. And we can see the amplitude modulation of the EFT burst, whereas at 2.5 gigasamples per second, then it's leveled out. So that's kind of a quick overview on something that actually happened in the lab when I first hooked up to it. And I kept it as an example because I thought it was interesting just how much oversampled it needed to be. And a related note, because we're talking about a horizontal phenomenon of sample rate, is that it's also an issue if the vertical scaling on a EFT or ESD pulse or even a surge pulse is captured. And this also applies to every type of waveform that every scope in the scope industry, the digitizer range is typically the full screen vertically. So in this case, if you had, for example, an 8-bit scope, then if you capture an ESD pulse and it's fills most of the screen, then you've got 8-bit vertical resolution. You're applying those 256 quantization levels to the pulse. In the case of if one were to capture a pulse and only fill half the screen vertically, then the number of bits would divide in half because the digitizer on all scopes is still going to keep capturing this upper half of the screen, but there's no signal there. So it just consumes ADC counts without having signal there, so you lose signal to noise ratio. So effectively, you'd have 128 counts of the ADC on the signal if it only filled half the screen. So that'd give effectively a 7-bit resolution. And then if the signal filled even less of the screen, like in this case, now it's filling about 4 of the grids. So it's got 64 quantization levels being used. So that effectively is a 6-bit resolution, even if you started out with an 8-bit scope. And the sample rate and the volt per division setting. So the two issues with the first with the sample rate and the undersampling, that's an effect here in the analog to digital converter stage of the scope, and it's undersampled here so that digitized EFT pulse in this case didn't have enough samples to have a sample happen to land on the top of an EFT's pulse. And the volt per division setting affects both the amplifier stage and the ADC because the amplifier volt per division setting is determined by the scaling that you set, and then the digitizer captures whatever's coming out of that amplifier. So that's kind of a quick overview on something that actually happened, kind of a war story from testing with an oscilloscope. And I wanted to share that because it turned out that it's necessary to have about a 1/4 to million to 1 oversampling because there's 250,000 to 1 oversampling on the fundamental frequency of that EFT signal in order to correctly represent it.
Okay, thank you so much, Mike.
Thank you. Thanks, everybody.
Yeah, thank you. Our next speaker is Evan Allen. Evan, if you can unmute and talk, I'll
Yeah, that's
turn
me.
over to you. Give me a second here, please. Co-host. Okay.
All right, let me share this. All right.
Got it.
So this is a little more, well, this is a story from 15 years ago or so. So I don't have any real data to back any of this up in the way of scope traces and things, but I do have some somewhat interesting history. And I'm sure a lot of people might remember GSM from, it's was still prevalent in the United States back into 2019, and you get all that interesting noise and interference on things, and it turns out that that's not, it wasn't unknown when it was being created either. So this is a little bit more of a silly or lighthearted thing. This is literally the phone that I had 15 years ago. It was running at 850 megahertz. It was quite a nice phone. It ran for 2 weeks on a charge. I liked it. It did nothing but make phone calls and very poorly text. And of course, everything I have was salvage and still is. And so these were my very nice speakers that were fairly powerful and are still pretty nice to this day. I don't use them anymore, but I still have them. And this little thing is what caused most of the issues. So I actually still have this, and it's sitting right next to me. The little volume label wore off of it, but it was super useful to me having a desktop computer set up, and I can have a set of speakers, I can have a set of headphones, and switch right back and forth between them without dealing with drivers and USB stuff to deal with what the headset's using. But you can see that wire coming off of it is very, very tiny. And that's part of the problem, but not the entire problem. So the way that I hook this up and still do is that I like to have everything controllable from a single spot. And basically you've got computer, which has software sound for all the apps and for the entire computer as a whole. It's effectively like having different potentiometers in series virtually, and then coming out of it, it goes physically into multiple potentiometers in series, because then I've got this media hub that has a volume control, and then I have the speakers that have a volume control. And it's kind of hard to tell when everything, where you're muted. I'm sure people over, this pandemic have been on calls with people who are like, oh, sorry, I was double muted. I was muted on my headset, and I was muted on Teams, and I was muted on whatever. So I tried to do everything as simply as possible. And so I ran everything at maximum volume all the time, fully amplified, with the exception of this tiny little media hub. And so it has a button on it for switching between speakers and headphones. Inside of it, all it does is it switches the left and right channels, not even the ground, but switches the left and right channels from the speakers to the left and right channels for the headphones. And it doesn't connect anything to either of them when they're not in use. So it leaves them nice and floating and susceptible to interference as big, long transmission lines. So I would have my cell phone sitting on my desk in my basement, and everything would be on silent. Everything would be muted or switched. What I effectively did was I would mute the speakers by switching to the headphone input, whether or not I had headphones in it. And then all the audio that would be going to the speakers was coming from nowhere. So I wouldn't have to worry about anything on my computer making loud noises or things, and everything would be fine. Except if I left my cell phone down there, and even if it was on silent, I would hear noise coming through the air ducts, through the entire house, because the little tiny wires inside of these cables, which were basically unshielded, were picking up the GSM interference. And so why does this happen? Because it's, the GSM signals are running at 800 megahertz or so. So that's, what are you inducing and where? Is it resonance? It turns out, and I found a very interesting website, which it's written well, it's lighthearted, and it contains a lot of some technical data, but it contains a lot of social background and history on the subjects of cell phone signal design. And I find it very entertaining to read through. It's on gsmhistory.com here. Where I found my information was from Unintended Consequences, which they go into detail about how this interference that I'm sure everyone is pretty familiar with, I have a clip of it here if it plays through, but I'll try that in a minute, was known before it got approved. And in fact, it was most known in hearing aids because presumably nobody who had any of these test setups that were running on a bench is just a big mess of wires before the first chips were produced noticed this. And the problem is, as I say here, is that they're not constant data transmissions. It's tiny, tiny packets that are modulated in bursts by this TDMA feature that I'm not going to try to remember what that means right now. And they're amplitude modulating their signal. So you'll get some interference picked up and then it goes away, and then it gets picked up and it goes away. And the TDMA is running in human hearing range. And it sounds a little scratchy because it's not super consistent all the time, but it's not a consistent tone, but it is always there and you can hear it. So it's not the 800 megahertz, it's the modulation that the signal has. Let's see if this will play through. So I don't know if you heard that or not, but
No, we didn't. But see
okay.
if you could hit the little speaker on that icon and see if that's up. Turn it up and then try it one more time.
Yeah, I heard it, so I'm
you
pretty
heard it?
sure this isn't going through. Well, let me see if I can change the.
You might have to reshare, and while you share, check the box to share your audio.
All right, let me try that because this is going pretty fast, I think.
Yeah.
Advanced sharing options. Nope, that's okay. Share screen, this screen, and computer audio share. Okay. Am I sharing the wrong screen now?
Now we just see your name.
Great. I'm sharing the wrong screen now. There. How's that?
Now we got it.
Good. Let's try this again.
No, we don't hear it, but that's okay. We've all heard it. We know
Yeah. So one of the interesting things that I found over a very short amount of time of hearing this was that I could, and I'm sure many of you remember, you can tell if you're getting a phone call or a text message because the sound is slightly different. And you can tell when the call starts to connect before the cell phone UI pops up anything. So I could pick up my phone and then a second and a half later, it says a call is coming in as I'm waiting for it because I know it's there. It's just the UI hasn't kicked in yet. Or I can hear a text message come in before the notification sound, which I thought was entertaining. But it is a problem if you have this in systems that you're trying to take data on, or if you just don't want to hear it. If you're trying to listen to something or watch a movie and this is coming on, it's a bit of a pain. So for me, the problem solved itself when the GPRS stuff stopped being used in North America in 2019. It's possible that I could have used better shielding on these cables. I have certainly modified my own devices.
We have 1 minute left, just so you know, 1 minute left.
Sure. I've certainly modified my own devices with upgraded cabling or electronics or bypass capacitors before, and that wouldn't be a problem. If instead of muting the speakers by switching the input and effectively leaving the input to the amplifier that is turned all the way up floating, I could have just turned the volume pot all the way down, which is just a 270-degree pot, and then they would have at least been terminated at ground. or if I change that switch for one that was double pull, double throw, then whichever input wasn't being used or output wasn't being used could have been grounded, might have been better. But an interesting video I found from Texas Instruments in 2011 is that this Johansson dielectric company was trying to sell these X2Y EMI filters, which, as they'll say, are similar to feed-through capacitors, but not quite, in that they have a input and output return signal, or input signal and return path, that are coupled across a ground rather than feeding through a capacitor. So you probably don't need those anymore, but it's an interesting solution to a problem that may still come up with other modulated signals. So that's everything.
Very good. Thank you so much for the presentation. Next on the list here is Karen Burnham, and Karen has a presentation on NASA EMC. So Karen, just talk a little bit so you pop
Okay.
up here.
Sounds
There you
good.
are. There you are. And I'll make you a co-host. Okay.
Okay, share screen, that one. Share and okay, so this is a story from when I very first became an EMC engineer at NASA Johnson Space Center. So this is, yeah, if one of the speakers is like, I'm not proud of this, but we wrapped it all in aluminum foil, that's about the level that this is going to be at. So up until this point in my career, I'd mostly worked in software, I'd worked with signal processing a lot, but then I got pulled into the EMC group at NASA Johnson Space Center led by Bob Scully. And it was really cool because I got to work on NASA standard initiators. I'd actually already been working on them before I joined EMC. These are the little, it's a little essentially bridge wire explosive device that then sets off the, the real explosive device, the nuts that, separate the space shuttle, or the gas mortars that push out the parachutes. And obviously, they're the weak link in the chain from an EMC point of view, because they're the one thing that's actually could be vulnerable to radio frequency interference. And we had a lot of information about how the NSIs, NASA standard initiators, reacted to Apollo frequencies, but not so much to shuttle and, or actually, no, we had good information on shuttle frequencies, but not for Orion and the International Space Station. So we needed to update, basically redo some studies that had been done before to figure out, do they have susceptibilities at these frequencies? And it was UHF and S-band. And here's just a little cutaway of what it looks like. And the thing to note here, it is a 2-pin hot and return. You just pump power through, it hits the bridge wire, heats up the bridge wire, and that sets off the rest of the reaction. It's a really simple circuit. It's a 1 ohm bridge wire. And the idea is that you can pump 1 watt of DC power into it and it should not fire. But if you exceed 3.5 watts, it will fire no matter what. So that's kind of the limit we were comparing against. Let's see, skipping ahead. So basically the issue was that Bob Scully gave me a test diagram and it looked like this. And then he promptly went out on medical leave for 2 months and left me in a department that I didn't know anybody, and I'd never worked with RF hardware in my life. And so I was like, okay, I'll go get an S-band, power supply, and I will get, the NSIs. We had them all nicely, contained in safety equipment and everything like that. And then I'm looking at a coax and I'm looking at a 2-pin NSI interface, and I'm like, these two things do not go together. I feel like we skipped a couple steps here. And so this is what the test setup ended up looking like. We need a signal generator, we need an amplifier. We had a bidirectional coupler so we could see especially how much power was getting reflected off the interface. This let us do some tuning, trying to minimize the impedance mismatch, which is of course insane. The adapter is the part I'm going to talk about, and then there's the NSI itself and its monitoring equipment. So obviously you can see everything up to this tuner point is coax. but then we need to get to our twisted shielded pair, which is how you usually set off an NSI. So figuring out that adapter was basically one of my first EMC or RF challenges. I tried a lot of different things. I did a lot of reading, and I tried, like I say, a whole bunch of different stuff, but I really did not know what I was doing. So with the UHF, it wasn't that bad. So in the 400 megahertz, I took an N adapter, tied the center pin to both the inputs of the NSI, and then got the outer case of the NSI to contact the outer shield of the N connector. And the reason that works, because you're like, didn't you just short the bridge wires together? How could that possibly still function? It turns out that at RF frequencies, NSIs are actually more sensitive to energy coming in between pin to case instead of pin to pin. The pin to pin, it really needs a lot of power to start to heat up that way. It's looking for that DC input. But here you can start sort of sequentially building up power in the explosive mixture and starting to heat it up that way, essentially. And we think that that's what the firing mechanism ultimately is. So, okay, so that kind of worked for UHF. At least it worked well enough with the equipment that we had. But then there was S-band, and trying to get that much, 2.2 gigahertz power into a wildly mismatched interface was an absolute nightmare. So this is the drawing that I came up with of a custom made adapter. So not so much with taking two existing things and then using some foil and zip ties. We actually ended up having this machined. And basically, again, so what I tried to do was take an SMA connector, the shortest possible one I could find, take that center pin, matched the dielectric of the coax with the dielectric inside the adapter, tapered the connection instead of trying to go straight out and then T-barring across it, basically trying to make the geometry of it as gentle a transition as possible. And I'll be darned, it did end up working. But the other thing that really made it work was just a way bigger amplifier. Basically, in building 14, which is where this work was done at Johnson Space Center, the basement areas, there's some shield rooms down there, and then it's like the Raiders of the Lost Ark down there. It's just equipment that people have dumped since 1961, and they just left to gather dust. And basically, it's where I learned the skill that I feel is one of my core skills as an EMC engineer, which is being a scavenger and just looking in every single corner you can find to see if there's any equipment that will possibly be useful to you. And it took weeks, but I did finally find in the back of a very high shelving unit, way in the back on one of the top shelves where no one could see it, a much more powerful amplifier with the correct frequency range. And that let us essentially, and I'd like to take some credit for the adapter, but with the adapter and with that amplifier, we were finally able to get the NSIs to fire with S-band power. Now, nowadays, I know that I can call up any old company and get a 2-wire to coax adapter. I really wish somebody had told me that back in 2011. But in the end, this was a successful effort, and we did actually show that the NSIs are particularly sensitive to some of the ISS communication frequencies. They can be set off with relatively low power levels if you give them a certain amount of time of exposure. And so that was actually, in the end, we actually got very useful information, and that paper has been cited numerous times as people have continued to evolve the use of NSIs in different programs. So yep, that's it for me.
Hey, Karen, quick question. Is an NSI like a squib in automotive?
Yeah, exactly. Yep.
Okay.
Although, yeah, people would say, "Oh, it's just a squib," and I'll tell you, the pyro test guys, one time they put one out in free space and just set it off with no protective equipment around it.
Yeah.
And that thing shot out a jet of flame 6 feet long.
Ooh,
Just
sweet.
by itself. I was like,
Sweet.
yeah, quote unquote, just a squib.
Just a squib. Okay, thanks again. Our next speaker is Arnie Nielsen with a taillight assembly EMC issue. So I found you actually. I'm gonna make you a co-host, and anytime you're ready, Arnie, it's all yours.
Okay, let's see. Can you see this?
I see you.
Uh-oh. You don't
You
see
gotta
my-
go to the bottom of your screen. There's a green.
Oh, yeah.
You
Okay.
mouse down. It says share screen.
Yeah, I got
So, and then pick one. It'll show you a bunch of different screens you can share, or tabs basically. And pick the one.
it. You see that now?
No,
You see that?
no, we see you. Try it again. Go down to the
see me.
green share screen. I'm pretty sure I've got you as a co-host.
Oh, here it is. Okay, I got it.
Yeah,
See it
yeah.
now?
Now we do. So now you probably want to make it
Yeah,
from beginning, maybe that one.
exactly. Okay,
Okay, go ahead.
okay. You don't want to see me sitting there in Florence, Italy, having a good time.
No.
I'll make this quick. This is a taillight assembly. Boy, taillights aren't like they used to be. They're pretty complex. In fact, you can see on this one, it's got a radar unit in the center and a bunch of LEDs in this little on the right side. there.
Arnie, we see your first page only.
Search
I don't
for-
think it started the slideshow, or we're on the sharing the wrong screen, one of the two.
You see that?
There you
Now we
go.
see
We'll keep-
figure
we'll keep to
one.
that. We okay?
I think so.
Okay. So you can see on the right picture, here's the power supply for all the LEDs in this thing. It's got a bunch of them. And of course, the problem was emissions. So here's just the part of the circuit that turned out to be a problem, just a standard circuit. So this actually turned out to be a pretty simple fix. Here's a blow up of the board with the screen shielding cover removed. And so what I did is I put a little pot on there, 20-turn pot, to change the resistance on the FET gate, standard fix, and it works like a champ. In fact, here's the pictures showing the standard resistor they had in there was 100 ohms, which is shown on the top. That's the drain of that FET. And you can see as you start increasing the resistance, that gets more and more rounded off. In fact, on the right picture there's a 300 ohms. And here's the actual, I think it was around 20 volts. Here's the actual pictures of the power supply going to all those LEDs. You can see how increasing that resistance made it a lot better. And here's my old Franken-Tem cell, call it. I presented in the January presentation.
Mhm.
So I stuck it in there. There's the top pictures with the door open. And the bottom picture is the with the door closed with this $300 EMC clamp on it. It really, you need that to really block out everything that's in the area. And here's the results from my trusty old RSP-1A that we talked about a little earlier with Karen. And you can see there's a pretty big difference in the emissions. So that was a zero cost fix, and it didn't cause any excess heating. I was surprised to see that. So I just checked, by the way, the ham outlet has these RSP-1As in stock again. They were out for a while. Yeah, the price has gone up a little bit, but it's still $139. Still pretty cheap. So that's all there is on that one. It's a pretty straightforward fix. I can go on to my second one because I'm going kind of quick here.
Okay, go ahead.
This is another one. This is off a 48-volt mild hybrid system. You can probably tell what kind of vehicle it is by that little symbol there. Actually, I didn't know these systems existed, a mild hybrid. So they had a bulk current injection problem. Here's the setup. So here's the battery pack. Here's the bulk current probe. It's about 150 megahertz. Now here's one of those issues that it's a spec issue. It's not a real world issue. In fact, I got coming in the next edition of In Compliance magazine in April, I think, that talks about all these specs and how much safety margins is in them all. So we spent a lot of time. It's good for business for our CMC consultants chasing things that aren't real, but they fail a spec, fail in quotes. But anyways, the fix was pretty simple. In fact, we tried a bunch of things. Here's some of the circuitry. Now, fortunately, I didn't take a picture of the actual fix, but it turned out to be very, very simple. It's basically put just a small 1,000 puff cap from the digital ground to the housing, which sounds easy, but this thing was in production or very close to it. So getting a reliable connection turned out to be the challenge. That took a lot more effort than finding the fix. So those are two straightforward examples of problems I've recently worked with. So that's it. I think I came in under my limit.
You did. Very good. Thanks, Arnie.
Okay.
So Kim, we're going to do the tower terror last, you said? Is that right? Kim, you're muted.
Yeah, let's do that last.
Okay, so let's go to your Tingle of Excitement presentation then.
Okay.
Do you need me to help you? Do I need to have you share? Make a co-host maybe? Okay, no, Kim, you're a co-host.
Okay, and Arnie needs to unshare, I think.
Yep, I just took his off.
Okay. And so you should see mine. Let me get this one into presentation mode here so it makes a little more sense for everybody. Okay.
Can everybody see Kim's? Because I still see Arnie's on my other screen here. Something, did you change something, Kim, on your end, or?
I did. My system thinks it's sharing, but I'm going to stop share now.
Yeah, looks okay now.
Okay.
I'm going.
Let's try this one more time.
Okay.
And I'm going to. Okay.
Yeah, now it's working. Can everybody see that now? The Tingle.
Yeah, we got it.
Okay.
Okay.
It's working now.
So there we are. Sometimes when you're in the field looking for a problem, you get this little sort of a psychic sense that, ooh, something's going on here that I didn't really expect. That's what happened in this particular case. The mystery turns out that there's a production module going out of a factory, and it checks out perfect in the factory on the floor, but when they unpack it in the field, it fails all the tests. And one of the first things they suggested was, oh, we probably have an ESD problem. So even though the manufacturer of the packing material for these modules claims that it's absolutely not an ESD problem packing things in their pacified styrofoam, they said, we're doubtful. We have serious concerns because we're getting these failures and we can't explain them. So they asked for a visit to the site to diagnose the problem. They can never accept diagnosing over the phone. You got to be on the site. And in this case, it actually turned out to be a good thing to be on the site. The site turned out to be in rural Indiana in mid-onion country. And I say mid-onion country because Van Wert, Ohio, was right in the middle of lots and lots of huge fields of onions. And this is the time of year when they harvest them. So it nearly knocked me over the first time I got into that area. And there you see the little town of West Vert, Ohio, and it's not
Van Wert.
It's not Van Wert. Yes, yeah. It's not very far from Detroit. It's a little back roady for a while, but not bad. And in fact, that's the back road it's on right there. So you can see a lot of those fields around it. All that's onion fields there. Okay, so it's an Eaton plant, naturally, because I was working for Eaton at the time. And a very nice plant, actually, fairly modern. And the first thing I do whenever I get to a plant, and this is a piece of advice for everybody if you're doing field work, find the local site technician. Find the guy who maintains all of the electricity and the electronics in that building. He's the guy that's probably going to help you out the most. And of course, all of us guys going in the field really hope we're going to discover that our electrician on the plant looks like this. Well, that ever happens to somebody, let me know. I've never seen it. Usually this is what the guy looks like, but he can point you in the right direction. And that's the important thing. He can steer you clear of a lot of false leads. And this guy really, really was helpful. So I went around with my trusty little static electric field meter, and I checked, and I found, sure enough, the packing material was not a problem. I could rub things across it all day long, and I wasn't developing any triboelectric effect and generating static electricity. So, okay, that was out. But I happened to be walking around the floor where all these lovely ladies were busy wiring up and soldering things. And everything was looking very, very copacetic. And I got to a place where I paused and I rested, and I happened to put my hand on two of the benches across the aisle from one another. And then I got that tingle of excitement. You know, when you feel a little electricity running through your body, and you know that there's something there that shouldn't be there? Well, that was it. So immediately I contacted the plant electrician again, and he and I came over, and he felt it, and he said, yeah, I feel the same thing you did. Well, he said, it's a little stronger for me. Maybe his fingers were a little damper or something. But we all know how wiring should be done in a house, for instance. You've got the three phases coming into the panel. It's distributed out in a neutral and a hot, and the third wire always goes to ground. Well, in an industrial environment, it's very much the same kind of thing. That neutral line ties to ground. And the electrician told me that a few months ago, they'd had a couple of engineers come in from a supply company that had rewired the entire plant for a whole bunch of new machinery they brought in. And these were professionals. They knew what they were doing. So he and I went around and we checked, and sure enough, everything looked good. And I said, finally, you know, Stan, his name was Stan. I think his name was Stan. We got to go to the main transformer and just take a look and see what's going on there. And we did. We went to the main transformer outlet and we looked at it and we said, hey, you know, lines 1, lines 2, and line 3 are all within a few tens of % of one another as far as load. It looks like it's been balanced very nice. And I said, well, let's do one more check. Let's check what's on the green wire neutral. He said, well, we're never going to see anything there, right? It ought to be no current at all. So we put our clamp-on meter on that line, and sure enough, 40 amps. Whoa. Okay, we didn't find a static electric problem in that plant. What we found was an inherent wiring problem in that plant that was somehow defeating the module integrity before it got packaged, probably near the last stage. I didn't stick around for them to rewire all that machinery, but after I got back, I called back to the plant and said, how are things going? They said, fine, everything's shipping out and it's getting there great. Whatever you did or didn't do, it seems to be okay now. So that's a easy case to solve, but a couple of talkaways. First, always talk to the plant engineers. I've found that 9 times out of 10, those guys can point you to the solution right away because they know what it is. They've told their management about it, and management has ignored them until they bring in a, quote, expert who lives at least 50 miles away. Second of all, assume nothing. Assume absolutely nothing. Check everything. Trust, but verify. Okay? And we will take questions at the end. And that's it, Scott.
Okay, Kimball, thank you. Our next presentation is going to be from William Sommerville. So William, please unmute again so I can find you here on my screen. See where you're at. Oh, there you are.
Share screen. Yep.
I'm going to make you a co-host again.
You guys hear me okay?
Yes, we do, and we can see it now.
Great. Yeah, I have a hard time following up that vocabulary extravaganza. Copacetic is a great word. I'm not sure if I can come up with a word like that. But all right, so here's round two. This is a little bit more modern. I mean, the last example I gave was 12 years ago. This is just a few years ago. It has to do with USB. And so, yeah, where I work now is a industrial augmented reality company. I'm going to go ahead and put my shameless plug in here. We are hiring. We're looking for software engineers and application engineers and others. So we are doing augmented reality in a wide variety of industrial applications, projectors, 3D cameras, other kinds of vision cameras, helping people do work in manufacturing plants, including Van Wert, Ohio, which was really interesting to see that town come up because we're operational there as well. And so what we have are a lot of PC-based systems. There's a PC in the middle of every one of our deployments running our software, and a wide variety of other hardware that we have to talk to, including torque tools, barcode scanners, projectors, all kinds of things. But what I'm going to key in on today is the 2D and 3D vision cameras. We do a lot of webcams. We do a lot of 3D USB depth sensors. And so this is an example of what like a hardware layout might look like. We have some parts that are on a factory floor. We have projectors projecting on those racks, and we'll have cameras. I don't see my mouth, but there are some, the white objects toward the top are projectors that are projecting light, and then the darker objects down below are USB cameras that are depth cameras. They're usually using 850 nanometer infrared light, either structured light or time of flight, different mechanisms to measure depth. But they can tell when your hand is going into a bin or touching an object, and then our augmented reality can react to you doing something. So we can make it an interactive air proofing system. So we installed a system in a warehouse here in the Detroit metro area, and we were experiencing some intermittent random camera failures. These are 3D depth cameras, and they would just suddenly stop working at random intervals, not within minutes or even hours, typically within days. And so we did all the usual things that you might do. We replaced those cameras. We replaced the cables going to the cameras, the PCs. We added an uninterruptible power supply in case there's any brownouts or spikes or anything on the power lines going to the PC. Updated all the software firmware for the PC cameras, et cetera. And nothing worked. And so there was only one other explanation, which is ground loops. We all love a good ground loop. And so this is a little bit of a very basic architecture of what that might look like. We have our PC over here on the left, black box. We have a USB cable going to the camera. And if you know anything about USB cables, all USB cables carry earth ground as a shield. And that is the outside metal on every USB connector, whether it's male or female, that is ground. It's earth ground on the outside metal of the USB connector. And the camera mounts to a roof truss, in this particular customer's case. The roof truss is tied to building steel, building columns. It goes down and touches earth ground. Not necessarily a dedicated ground wire for building columns. It's just literally going into the ground. And then, of course, the building power that's powering the PC has earth ground. It's probably going to a ground rod, a power distribution panel. And so we end up with a loop. We actually end up with a complex network of loops when it comes to building structures. And there are some nearby radio towers and other interference sources that are picking up a lot of time-varying magnetic fields, that if you have a time-varying magnetic field in a continuous conductive loop, you will induce voltage, and that voltage that's induced completely negates the value of having a grounded shield on your USB cable. And I think these were USB 2.0 cables, so they weren't even necessarily very high frequency, 480 megabit per second. It's a USB 2.0 data rate as opposed to 3.0, which is 5 gigabit, which would be even more sensitive, I think, to interference. But certainly, if you have a ground loop, your earth shield ground on your USB cable no longer helps. And so if you look at a little zoomed in view here of our USB camera, this is an Orbeck camera, it's a Chinese brand, structured light, 850 nanometer depth camera. We had made a U-channel aluminum bracket around it with a rubber mat and a 1/4-20 steel screw holding that camera inside that U bracket. The U bracket is just to protect it mechanically in case, there's some kind of a high-low or other equipment moving around. If it hits the camera, it's going to hit the outside U bracket. And the rubber mat was there, not because we wanted rubber, but because we needed to hold this camera very snugly inside this U bracket. And we found a rubber mat on McMaster car that just happened to be the right thickness. But the USB grounded shield cable would come into the metal camera, and the ground would travel through this metal screw to this aluminum U-channel, and then to this mounting material that we used. It's a ball and socket type mounting bracket that goes to the roof truss. And so you had a continuous path from the USB cable through the camera, through the screw, to the aluminum bracket, to the roof truss. And so the answer was pretty obvious. We replaced that steel, like zinc steel 1/4-20 screw, with a nylon 1/4-20 screw, which is an easy trip over to Home Depot or Menards. You can pick up a 1-inch long 1/4-20 screw. We did that. We tried that out, and that fixed the issue. Now, the fun part of the story is not so much the ground loop, but we, we're a small company at the time. We found this nylon screw. We decided what the solution would be, and we asked one of our interns to take that screw over to the customer's site. And so this is an 18, 19-year-old electrical engineering Kettering University co-op student. We said, hey, take this nylon screw, drive over to that customer's site, and have them replace the steel screw with it. So we went there, and he went up to the union tradespeople there that own the man lift and everything, and said, all right, here's your screw. You put this up there, it's going to fix the problem. And they laughed in his face. They thought it was hilarious that this guy, who was obviously not very experienced, would hand them a silly plastic screw, and that would solve anything, let alone this very sophisticated augmented reality system where we're projecting work instructions on some pick bins. And so we had to take a minute and really just tell them, hey, look, it's not me, it's my boss. Like I don't know why this plastic screw is going to help you, but they told me I had to give it to you, and this is what needs to happen. And so they gave him a good hard time, and they got in the lift, and they were 20 feet in the air. They replaced the screw with a nylon screw, and guess what? It worked. So that was, one of our favorite stories to tell here at Light Guide is this time. And then, by the way, that student, he graduated college. He's now with us full time. We love him. He's a very great, asset to the team. But the story of the plastic screw that he had to hand the union workers, who were probably all triple his age, and convince them to get in the man lift and go up and replace it and solve the ground loop issue. And then moving forward, we ended up deciding we're going to use a 3D, we have a couple 3D printers here at work. We're going to 3D print all of the camera brackets moving forward. So this is the next generation of that Orbeck camera with the 3D printed bracket visible on top of it. And it turns out that not only will it break any ground loops that happen, which is pretty important for every kind of 3D camera that's a USB type, but also it gives us options. So because it's 3D printed, we can have threaded holes for our mounts to go into the top, to the back, the side, and have more options to be able to mount these different directions, as well as across the 5 or 6 different 3D cameras that we use. Every one of them via the 3D mount can offer the same about 5/16 thread hole that the ball and socket joint that we typically use to make all those cameras totally interchangeable, so we don't have to worry about differences in cameras mounting. So that's that story, and that's all I have. Thank you.
Okay, thank you so much. Very good. Okay, that brings us back to Kimball Williams with his computer screen nausea story.
Let me go ahead and share. Whoops. Why is it not?
You see it?
Yeah, but you see it not in demonstration. Oh, there we go. Okay. Now you should see the thing. Okay. This
we
is
still see it. We still see it not in presentation mode.
really okay. Let me stop share and then share again. Apparently, it's getting a little weird. Well, Zoom is always a little weird. Okay. PowerPoint. Okay, and that. How's that look?
Got it.
Okay, right. So, actually, the computers weren't being affected. It was the operators that were getting nausea. And let me see why it is not allowing me to advance the screen now. There we go. So, a mystery that we've got. New rooms to house 12 computer stations in a manufacturing facility. Set up, they put up the drywall, 4x2x4s, framed it in, wired it up, installed the computers. Everything seemed to be going good. All the new computer workstations and at this time, to tell you how far back it was, they were all CRT screens, and they all seemed to be operating normally, which means they turned them on. They'd got a screen coming up that looked right, and the keyboards responded. So everybody said, okay, we're ready to go. Okay, except the displays undulated in a little slow circling motion, sickeningly. And in fact, I sat down in front of one of these, and within about 20 seconds, I was beginning to feel upset to my stomach. The visual impact of this slowly moving screen when you expect it to be stable was just unbelievable. So that movement suggested we needed to do something, because they were going to get a whole bunch of operators that just threw up on their keyboards instead of doing any work. So let's find the problem. So ambient conditions, no significant RF fields found between 10 kilohertz and 1000 megahertz, and no unexpected low frequency fields are found at 60 hertz and its harmonics. You always expect to find 60 hertz anywhere on this planet. You realize that as soon as you think about the wavelength of 60 hertz, and then figure out how far away you have to be from a source in order to be out of the near field. And you realize you've got to be mid-Atlantic Ocean on a sailboat in order to be away from that. So it wasn't surprising to find some low frequency fields, but you always find some. Okay, however, a near A field test probe indicated unusually intense AC fields in a very narrow line across the back wall of the facility. And by the back wall, I mean running across at about desk height, across behind every single one of these CRT displays. And okay, what could possibly be causing that? Because all of the wiring for the inside of the room, according to the electricians that I was talking with the plant, was down underneath the table at about 6 inches off the floor, and I could see all of the outlet sockets. And they assured me no problem there. Okay. But looking on the other side of the wall, there was an Canadian aluminum conduit with a wire in it. And the conduit ended in an AC outlet. Well, this shouldn't be a problem, because in a conduit, you've got shielding. And the conduit just happened to be about the same height as the back of all those computer displays. So I'm thinking, okay, we've got some circumstantial evidence here, but how the heck could there be a problem? Now, we all know that wiring anywhere uses the 3-wire system as a minimum. And, you've got your white and your black, which is carrying the really juice. And then you've got the green wire or the unshielded wire, which becomes your perfect ground, your safety ground. And that's the way it's always done. Okay. However, my magnetic field probe was showing, whoa, look at that, around 120 Hertz or so. So there's something going on here that's weird, and I need to find out what it is. So again, talking to the plant electricians, I asked them, how is this this done? Is there Romax inside that conduit? They assured me, yup, there is. So the way the socket would be wired is the green wire would be going to a safety ground, and the white and the black wires would be going to the terminals, just like always. Not a problem. Everything should be fine. And that's what they said was there. Okay, I trust you. However, notice that now let me back up one here. Notice that this is a conduit going into a metal box, and the plate that holds this in place is held in place with metal mounting screws. And the black hot wire happens to go very, very close to one of those mounting screws. And they had a low resistance short caused by one of those wires being right behind the mounting screw for the front plate, penetrated by the tip of that screw and making a high resistance or low resistance, depending upon your how you judge those, a short circuit, but not a complete short at that point. Not enough to blow a circuit breaker, but it was enough to pull about 8 amps out of that wire and shove it back through the green wire grounding system on the conduit. So the conduit itself was conducting about 8 amps of current back along that pipe behind all those computer terminals. There was the source of our magnetic field. Well, that current flow was the culprit. So how do we get rid of it? Well, the simple way to get rid of it was go inside the box and reposition the wire and put the cover back on again. And for this, they paid me to travel to New Jersey? Oh, well. Anyway, sometimes you break even, sometimes you don't. Okay, so 60 Hertz magnetic field plus a 50 Hertz or about 60 Hertz refresh rate on those screens. Because remember, this is a CRT display. Every 60 Hertz is when the display refreshes, and it refreshed at a slightly different time for the interfering field, and that's what caused the display to undulate and move around. Instant nausea. Okay, and we're going to leave questions to the end. So, Scott, that's it.
Okay, thanks, Kim. So it looks like we're to the bottom, so we're going to back up the list now to the Tower of Terror. So Kim, if you can turn on your slides, Kim and I are sharing this presentation, so I'm going to give you the background information and set it up, and then Kim is going to take over at some point here.
Ooh, I've got to find my Tower of Terror stuff.
Okay.
Hang on, I've still got a presentation that doesn't want to quit. Okay, there we go. Okay, oh, Tower of Terror, there you are. And close out 1. Close out 2. If I can get it to close out. No, I don't want to share that. Hang on. Unshare. Because I don't want extra things running. It confuses my computer when that happens. So share. Where did my, oh boy. Sorry guys, I'm having a senior moment here. Learning how to control my computer again.
No problem.
Okay. So I can go into full screen mode and then
I see something.
How's that
Okay.
look?
It looks good.
Okay.
Okay, I'll start here, and then we're going to turn over to Kimball somewhere in the middle. So this presentation is about theme park. It was at one point called the MGM Studios for Disney in Orlando. I believe they've since changed the name. It's down at Disney World. And back around, I think Kimball was it 1994? You know the year?
Something like that. I've forgotten the year.
Around 1994, maybe a little later, maybe a little earlier. They made what's called a drop ride down there. And the drop ride is called the Hollywood Tower of Terror. And it was based on Rod Serling's television series, The Twilight Zone, those of you that are old enough to remember this stuff. And then 10 years actually after they built this one, this was the first one they built similar drop rides in Disneyland in California and in Tokyo, Japan, and finally in Disneyland Paris. Since then, in 2017, they've revamped the one in California to Guardians of the Galaxy. So the ride is basically a bunch of elevator cabs that are, there's 4 where you load the different people that come to the ride. There's 4 loading cabs, and then the cabs move in and out of the horizontally in and out of the elevators. And there's an example of one of the ride cabs there. And they move into what Disney refers to as the 5th dimension. So the illusion is, and Kimball and I don't get the illusion because we know how it all works, but the illusion is that your elevator car is floating through space. So unfortunately, when I went on the ride, I didn't get that. But so at some point you float through space, and then Disney has their various tricks that they use, okay? And you have an illusion that we actually didn't get. But the fundamental thing that goes on is the elevator cars are automated vehicles that was made by Eaton Corporation that Kimball and I worked for Eaton back at the time, and they made these cars. So again, there was 4 shafts that go up, and then you go horizontally through, and then you get into another elevator shaft, and that's called the drop shaft. So these drop shafts, once you get into that one, have gigantic motors on them, which Kimball will show here in a minute. And the elevator drops 39 miles an hour. So you're actually dropping faster than gravity at some point. So you feel like you're weightless. And since Kimball and I went to the ride, they've actually programmed these drops so that you get multiple drops. So originally it was like 1 drop, and now they do multiple random drops. So if you go on the ride, Monday and Tuesday, when you go back, it's going to be something totally different. Each one of these rides seats 22 guests. So the building itself on the drop elevator side is 199 feet tall. So it's the 2nd highest ride in Disney World. Expedition Everest is 199.5 feet tall, and the Dolphin Hotel is actually 257. So it's one of the tallest things you'll see when you drive down to Disney World. The drop elevators, the 2 gigantic controlling motors, are 12 feet tall, 35 feet long, and each weigh 132,000 pounds. And again, they can move the car 39 miles per hour. So these variable speed drives use PWM, and that is what begins to cause the problem. The ride itself, as you're going through it, uses some of the Disney tricks called forced perspective and Pepper's ghost, and that creates all the illusions, of ghosts floating around and that you're going down super long corridors that you're not really going down. Otis Elevator actually made these, but we couldn't call them elevators, at least at the time Kim and I were there, because it kind of violated every rule you could think about for an elevator. So it was not classified as an elevator at that time. And at this point, I will turn it over to Kim and he'll explain what the problem was and how we went about solving it.
Okay. The devices that actually carried the passengers around were based on these little industrial well, not so little industrial robots that are designed to be controlled by a computer in a plant and use these high bay storage facilities to put boxes into particular places. And the computers know where every single one of these is because it's following tracks on the floor. And the floor tracks pulse a magnetic signal. If it's a kilohertz, it's a 0. If it's 900 hertz, it's a 1. And so it uses very slow digital communication magnetically through the floor track. And that allows both communication and for accurate positioning or recognition of positioning of each of the robots, wherever they are. Now, we all know that a signal goes down and a signal returns, and that, of course, is the principle for most electronics. But if you decide that you're going to do signal down and then a signal back by making a very, very large loop, then you may have created something different than a simple return. You may have created a big antenna, and that's actually what happened in this particular case. Whoa. I can see I'm getting off track here, and I'm going to have to bounce around a little bit. Sorry about this, guys. Anyway, the robots ride on top of the floor, and they have sensors that look down and they read the magnetic field from these wires, and that's cool. Okay, but in the Disney World facility, after the electricians installed everything, they came to us and said, "But it doesn't talk to the computer. It refuses to hear the computer, and the computer doesn't know where it is." And so when Scott and I went down there, we went down knowing that we had to look for a couple of specific things. By the way, you notice that the Disney uniform for engineers, an orange hat and a bright red and black coat, and that was typical uniform. So when Scott and I got down there, each of us wearing our yellow hard hats and our white lab coats, they immediately dubbed us as the Ghostbusters. Okay, back to basics here. If you've got two things that are trying to talk to each other and you have an electromagnetic wave coming in from the outside, obviously you're going to get some loop induction there, in which current in the top loop goes one way, current in the bottom loop goes the other, and you've got circulating current, which is a nasty interference problem. Okay, well, we obviously solve that simply by buying our cables with twisted wire pairs. And that gives us an automatic cancellation. I think it's something like, if I remember Henry Ott's first book, it was something like 13 dB of reduction just for the no cost factor of doing a simple twist. And for all of these robots, the simple way to do it is the primary line that the robot follows is a straight line to wherever it's going, but then the return signal goes across to the other side, goes down, goes across to the other side, goes down, goes across to the other side. And of course, every time it crosses, it's going to cancel out or at least give us a substantial reduction. Now, let me play around because I see now that my discussion has gotten us out of line here. So I need to go back a little bit here to this. Instead of following the instructions that the company, at the time it was called Kenway Robotics, instead of following the instructions by laying a ground or a directional line on the floor and then cutting lines in the floor to allow the return line to come back and crisscross and cancel out, the Disney engineers said, let's simply put that line that goes on the floor to the end of the hall, and then we'll run it up the end, and then we'll run it across the ceiling, and we'll run it right back down. Yeah, simple, right? A lot easier than all that crisscrossing wire on the ground. Why would they want to do that anyway? Well, we found out immediately when we got there, because it was Scott's idea right away, is let's just connect an oscilloscope and see what we see. Well, we knew what we should see, relatively quiet, and then a 900 hertz and a 1 kilohertz signal, right? Okay. Okay, so we saw this kind of stuff. And I think that first day we got there and we looked at this and we said, oh boy, we got a problem. And we didn't go much further than that night. We set the equipment aside, went out and had dinner at the hotel, had a good night's rest, came back in the morning and turned it on. And sure enough, again, there was all sorts of noise on the oscilloscope screen. But it got much, much louder at the same time that we heard from halfway across Disney World area, and you know how big Disney World is, we heard somebody fire up a skill saw at one of the construction sites, and the screen went just crazy with noise. Okay, well, obviously what these guys had done was built one of the world's biggest loop antennas, and it was going to pick up everything in the surrounding territory. So when we finally got a return path corrected and taped down on the floor as a demonstration run and took a look at what the scope gave us, okay, now this is stuff we can live with. That's reasonable. So that solved the problem. Okay. And from that time on, the Disney folks enjoyed their scare as they got dropped, which they did every time they rode the ride. I rode it once, and yeah, that drop is scary. And at the end, they even have some 3D holographic projections of ghosts. And that's interesting too, because 2 of the ghosts turn out to be sitting beside you in an optical illusion. And Rod Serling isn't there, but if you ever get the chance to get off on the 13th floor of Tower of Terror, you'll probably meet him. And that's it.
Okay, thanks, Kim. Now we get to the questions. So you are, please unmute yourselves and tell us which speaker your question is for, and go ahead.
Thanks for that Mickey Mouse presentation, Kimball.
Very good, Steve.
I do remember lunch with Snow White was spectacular.
So I guess I'll ask a question about that last one. What was the reaction from the people who would then have to go and embed that wire back in the floor that they already finished?
They actually hadn't finished the floor, which usually is a very nice smooth coating over the top of it. It was bare concrete when we got there, but they only had one wire line cut in the floor to drop the wire in. They had to go back and put in all of the others crisscross, and they didn't argue because we showed them the difference and why they had to do that. And they were convinced. You know, we had an airtight case there. And besides, Scott's a great salesman. He could convince anybody.
Oh, sure, Kim.
Question for Christopher with the oxygen sensor. Christopher? I guess Christopher is not there.
I'm sorry. I think I was the PMIC with spread spectrum. I think you might be talking to Will.
Will, my mistake. Thank
No
you.
worries.
Yep. I'm the oxygen sensor guy. Yeah, that's right. Yep.
Yeah, great, good. I was just curious. You had the oxygen sensor mounted where it needed to be, but was there any consideration of, instead of running an analog signal to the PLC, could you have digitized it, maybe a Modbus sensor there, and then run RS-485, or maybe even serial over fiber? Were those options at the time?
You know, that was a good idea. So what we did, we put an amplifier very close to the sensor and had a 0 to 10 volt signal that ran a longer distance out to the PLC input card. And so, yeah, one of the options, we made a very short line. We shortened the line as much as we could on that low current kind of raw signal line going to the amplifier, and then we increased the amplifier gain.
Right.
But then we did have an analog signal that ran probably 30 feet back to an analog input card. It was like a Siemens, like a 316 PLC with an analog input card on it. And you know, if we weren't as far along as we were, that would have been a great option to digitize it and just, you know, come up with whatever, RS-485, fiber optics, something, and not have any more analog after the amplifier. We just assumed that once we amplified it to a 0 to 10 volt signal, that no amount of interference would get picked up on that.
Right. You already started on the analog path and kept amplifying. I can understand. Makes sense. Thanks.
Any more questions?
Not a question, but a comment. Scott, next time what we ought to do is suggest that anybody that has a question as the speaker is speaking to drop the question into the chat. That way they won't forget about it.
Oh, yeah. That's a great idea, Kim.
A little late, but...
So what do you guys think of this? Think this is something that we should do once in a while? Is this a good format?
God, I think you pulled off a miracle that we're not still here until midnight, and that everybody actually like expeditiously went through their talks. Thanks, everybody. That was awesome.
It's the St. Patrick's Day miracle.
Yeah, I've never seen that happen, and I'm blown away by that as well. So good job to the moderator.
Okay. Thanks, everybody.
I don't know if you can you hear me?
Yeah.
Yep. Go ahead.
Sorry, hello, everyone. Just want to say, hey, Scott, it's everybody. This is Rob Cato. Sorry, I'm sitting on my back porch, just listening on the phone, drinking a Guinness, enjoying the weather. But I just want to say thanks to all the speakers and nice work. I echo everyone else has said, and nice work with the moderation of keeping the time.
Okay. Well, we appreciate the feedback. Yeah, we're doing good. We usually try to have this all wrapped up by 7:30, and it's 7:26. So I think it was a miracle. It definitely was a miracle. I just want one quick announcement before we go here, and that is EMC Fest 2022 is still on. You'll be getting an announcement as soon as I get some feedback from the hotel. We still want to get the hotel rates and the link, and as soon as I have that, I'm going to send it out. So I'm hoping that's within the coming days. You'll be seeing the announcement for EMC Fest 2022.
And that's expected to be May, not September, right?
May the 12th. Please
Awesome.
reserve your calendar now for May the 12th. It's in Livonia, Michigan. So I'm going to mute myself here, but if you guys want to do any, I know we cut out network timeout. If you guys want to network and chit chat, I will keep this open for you guys.
I do have a question from Mike Hertz with the oscilloscope. Is Mike still here?
I see him. I see Mike is here. There you go.
Mike, I was very curious about your results with that 2 gigahertz sample rate versus the 250 megahertz sample rate. And there's a big price jump between the scopes that can do one and the other. And it was very worrisome that one would see some sort of a signal on the 250 that then disappears at the 2.5 gigahertz. I'm not sure I understood how I could get that. What was causing that? That would be very worrisome to be getting the wrong signal out of my scope.
Sure. Yeah, basically the source of the issue was that because EFT pulses have such as a fast pulse width and a fast rise time relative to their frequency, then effectively they're extremely low duty cycle signals. And so for a very low duty cycle signal, then what we're considering is the rise time of that fast pulse and having enough sample points that samples happen to land at the crest of the pulse. So normally for Nyquist, when you're oversampling by a factor of 2 to 1, it's relative to the highest frequency. But in this case, the EFT pulse has a low frequency, but also extremely low duty cycle, a very high signal frequency that makes up the rise time. And so that short pulse width and the fast rise time is effectively a high frequency signal. So the high sample rate.
So
go ahead.
Would it be fair to say that that might have been a gigahertz frequency, or maybe a gigahertz and a half, if one was to measure it in the RF domain with a Fourier transform?
That's right. Because since signals are made up of a sum of sine waves, then the portion of the frequency content that made up that extremely fast rise time was a higher frequency signal. So like you said is correct, is that it could be that when we account for those sine waves that make up that very sharp rise time, they might be as high as 1.5 gigahertz, for example.
Thank you. That explains it perfectly. I did not see that before.
Yeah, thanks.
Thank you very much.
Good question. Thanks.
Thank you.
Yeah, it sounds like the base frequency is really a red herring there, right? I mean, it has nothing to do with the base frequency. It's all about that rise time.
That's right. Yeah, because that fundamental frequency is basically the pulse repetition rate, or the pulse repetition frequency in this case is 10 kilohertz, which is, it's kind of deceiving when we think about what sample rate we would need, because if all we considered was that pulse repetition frequency, we might think that a lower sample rate would be okay. But when I sampled it at over 10,000 to 1 oversampling, it still wasn't sufficient because of what Daniel said, that there's actually very high frequency content that makes up the signal, even though the frequency of the pulse repetition itself is quite low.
Well, I did write down my questions. Maybe that's why I have them still. I had a question for Joanna about the, oh, she's there, yay. Joanna, you're back? Yes. That was very good finding the resonance that was taking place, and then you put in 100 ohm resistor. If I remember correctly, you said the 100 ohm resistor at the input of the microprocessor got rid of the inducted power. Did I remember that correctly?
The idea there is that you're lowering the Q of the resonance circuit. And so hence, you dramatically lower the current in the circuit at resonance, and the problem goes away.
But you would place the 100 ohm resistor at the input. Is that, did I misunderstand?
Right.
Okay.
The input of the microprocessor is a capacitor. So I put a resistor in series with the microprocessor's capacitor.
Okay, yes. Now, would that be more of a pull down or a pull up that was taking place, or is it really just to the signal coming in from the
series? The only current that goes through the resistor is leakage current.
Oh, got it. Okay, so it's thank you. That makes a lot more sense. Thank you.
You're welcome.
Perfect. Joanna, the thing that really struck me about your presentation is you're talking about 2 picofarad capacitances, and that can happen all over the place. I mean, you can almost not avoid 2 picofarads under any physical scenario, right? I mean, 2 picofarad between any 2 objects at any distance. So it seems almost, if you have any IC, like a through hole, 8-pin IC, you're going to have 2 picofarad between any 2 pins. And so it was just amazing to me that those types of capacitances are the ones that you're dealing with from a resonant circuit standpoint. It's totally dominated by the inductance. The capacitance is just going to be completely unavoidable. And to think that you can get a resistor in series with that is pretty impressive.
You're completely correct. You can't avoid the fact that the gates of the transistors on a microprocessor have a capacitance, and that capacitance on, depending upon the node, varies somewhere between 5 and 10 picofarads. If you're talking about the old 4000 series CMOS, it can get up as high as 35 picofarads or so. There's capacitors everywhere. You have a off diode, showed right there in the data sheet, where there was 3.5 picofarads of capacitance across an off diode. There's capacitance across LEDs when they're off. And in fact, there's capacitance when they're on as well, but it's mostly overwhelmed by the effective resistance of the LED at higher frequencies. So yes, these capacitors are everywhere, and that is exactly why EMC is everywhere.
Yeah, I mean, you're not going to get rid of the capacitance, that's for sure. You can reduce the inductance, add some resistance, and that's about all you can do, it sounds like.
Well, what you do is when you have an issue, you identify the inductance and the capacitances within the circuits. And when you find a resonant circuit that has the right frequency, you know what circuit, where the RF current is going without doing any probing. You simply sit at your desk, quietly staring at schematics, and sometimes taking a tape measure to the actual device or a pair of calipers, and you measure what the distances are. You estimate the capacitances and inductances, and you fix the problem on your desk.
Just a related story to that, I've seen, just anecdotally in my career, people trying to shield circuits to prevent EMI, and then the shielding adds capacitance, and then you get a whole new EMI problem from your capacitance to your shields.
I hate ferrites. I hate shielding. I avoid both whenever possible. Do I use ferrite? Yeah, occasionally, but only very occasionally. And I shield almost nothing. And the way I get away with that is I simply understand where the current is going and where the current is coming from. If you keep the characteristic impedance of your transmission lines well below the characteristic impedance of free space of 377 ohms, you have significantly less problems with EMC. Okay, it's just physics. That's what I teach in my class, is just the physics, so that people can solve EMC problems at their desk before you ever build the first prototype. Design it right, build it, test it, ship it, go on to the next job. It's simple, it's easy.
Yeah, just keep your nice impedance mismatch, preventing that power from efficiently coupling into your system, and you're good to go.
Yeah, like look at these very fast transistors. They found that they had to have a bus bar to feed the silicon carbide transistors. Look at the Wolfspeed application notes. What that means is that the frequency content of what that transistor is sucking down through those conductors is so high that you needed a very low transmission line, the 2 parallel buses separated by a thin dielectric, in order to create a transmission line that was low enough to have an equivalent series inductance that was low enough so that you didn't get ringing. All of this is electrical engineering. All you have to do is be able to recognize where the capacitors are, where the inductors are, and to be able to estimate the capacitance and the inductance. And then EMC is easy.
You make it sound so easy, but I don't think a lot of the world sees it that way.
Well, 16 hours. I teach a class that takes 16 hours. I give a free 4-hour workshop after the class, and it teaches these techniques. And at the end of the class, I challenge the participants of the class to stump me. Bring me a problem that we can't fix in 4 hours. I dare you.
That's great. I really enjoy this session, you know, just being able to hear all these stories and all these first principles being applied to solve real world problems in ways that, you know, most of the world just would never even consider or have any real context to understand. So just very, very happy to be here today.
Would you guys like a freebie? A quick freebie?
Let's
I'd
do
like
it.
All right, let's see if I can, where's my screen? If I can find it. Somewhere. There it is. Okay, can you see it?
Yep,
Yeah.
I see it.
Okay, so had a client, had a big DC inverter, and they had a great big electric motor. They wanted to measure the current going between the inverter and the motor. Cool. Easy breezy, let's do this. And so they have a test box. And inside this text box, they have a bunch of high power RF connectors. This is one of those connectors. Okay, you guys tell me, why did this test box create hideously, amazingly high levels of RF? This is a quiz.
I see lots of pointy corners.
Someone speak up. Why did this test box fail miserably?
It's an antenna.
Oh, there's an antenna there. Where is it and why is it?
Yeah, they're not trying to control the impedance at all from the transmission line into the box and back out of the box.
Yeah, you have a transmission line, one of those great big orange cables. It's going to those great big, you know, coax connectors. And this is the inside of one of those coax connectors. And you see where that coax connector, where it has 4 holes. The technician building the box drilled 1 hole. You put a bolt through the hole, didn't bother to put a nut on it, and all the RF current that was traveling along the shield of that great big hunky orange cable was wandering all over the place and going exactly where it wasn't supposed to go. And that's why the room had hideous amounts of RF in the room.
Is this
As
at
you see
least
in
in
the
an
picture
enclosed
here,
metal box, or is this just exposed to the open atmosphere?
this was just a big metal box with a bunch of orange cables coming up to it. 3 orange cables on one side, 3 orange cables on the other side, and a way to measure the current on the inside. And the way they built the box, where the shield of the orange cable was not properly mounted to the box, caused the problem. There was RF current going back on the outside of the shield. Now, this is transmission line theory. And if you're going to do EMC, if you're going to design EMC compliance into your products, you have to understand transmission line theory. It's physics. It's easy. 16 hours is all it takes me. And you'll be able to do it too.
Yeah, we had that problem in a solar deposition machine because we were trying to couple our power into a plasma And we had transmission lines and splitters inside these vacuum chambers trying to couple power into the plasma. But the mechanical engineers had no idea what impedance was, had made no attempt to match the impedance of the transmission line of the plasma to the line itself. And so therefore there were huge standing waves, high voltage, high current all along the line. It would arc over and everything. And it was just about a 1-hour consultation where we worked out the impedances to the various portions of the line, made a few geometry changes, and all of a sudden the power coupled way more efficiently. There was no more arcing, no more high voltage sections, and everything was fine. But that was just because the people who designed this had no idea that radio frequency power had impedances and that mattered and that you had to try to match something.
Would you like, excuse me, would you like another freebie?
Let's do it.
Yes, please.
Okay, you got a PCB. It's square. It's tiny little beastly, and this tiny little itty bitty motor. You might remember the little slot car motors, little itty bitty motor. They're kind of like the same motors that you find in mirrors, in the mirror gimbals in automotive. All right, so the motor was connected to the printed circuit board. Cool. It failed radiated emissions at 1.5 gigahertz. It was a broadband emission. It was literally the noise from the brushes coming out of the motor. Okay, cool. How do we fix this one? Well, first off, we take a look at the physical dimensions of the printed circuit board and the physical dimension of the cable from the printed circuit board to the little motor. It was all 2 inches. Whoa. So what's the wavelength of 1.5 gigahertz? Well, you calculate that. It's almost 8 inches. Okay, it gives us a hint. So what's a quarter wavelength long? Whoa, 1.96 inches. That's really very close to 2 inches. So what we've got here is we've got, here's incidentally, if you want to do it in metric, the metric numbers, 50 millimeters.
That's what I just calculated.
Here. You go ahead.
I was going to say, yeah, I can only think in metric, but that's exactly what I just calculated.
Yeah, there you go. Okay, so you got quarter wavelength sides on the little square printed circuit board. The cable to the motor is a quarter wavelength. You have a half wavelength resonating structure. Think of it as an antenna where the source is inside the antenna. Cool. So what do? We take ourselves and we find a 1 gigahertz ferrite and we drop it on the board, but it's not going to work. Why is it not going to work? Well, it's because there's a parasitic capacitance there between the pads and the ground on the board. Can you calculate that capacitance? You betcha. You can calculate that capacitance. You can calculate the X sub C. You can know what that capacitance is and know what you need to do. In this case, what do you need to do? You have to evacuate the ground underneath the pad of the ferrite that goes to the motor. And by doing that, you remove the parasitic capacitance and you have all of the current, all of the RF current going through the ferrite, seeing the resistive nature of the ferrite. So, hey, cool, this works. Solve the problem. And all it cost was 2 ferrites per motor. There was actually 2 motors, and so 4 ferrites. Problem solved. It was a single pass of the board. You look at it, you diagnose it because you understand the physics, you make a change, you produce a sample, you test it, you ship it, you get it out the door, go on to the next problem. Understand the physics and put the probing away. Just understand the physics, get out your calculator, literally replace probing with an oscilloscope or probing with a spectrum analyzer with your calculator. And you sit there and you solve problems, EMC problems at your desk before you ever ship a single product, before you ever prototype a single product. Design it right, build it, ship it, go on to the next job.
You forgot the tape measure that you need to measure up the dimensions of things.
That's true. You do need a tape measure. Thank you. Well, actually, and a pair of calipers. Where's my calipers? Okay. I'm an electrical engineer and I keep calipers on my desk.
Yep, I have a tape measure I keep in my pocket for these kind of things.
My calipers are right on my desk too.
Are those digital calipers or are they analog calipers? We're electrical engineers, guys.
Excuse me. Okay.
Joanna, I have a question.
Yes, go for it.
Does 1.5 gigahertz come from brush?
Yes.
That means this frequency changes if motor speed changes.
Yes. But it's not, it's a broadband emission. Okay. It's literally the brush noise, but because of the parasitics, it's occurring at 1.5 gigahertz.
Yeah, think of it as an oscillator of sorts. I mean, an oscillator works by just basically electrical noise, which is very broadband in nature, and that's what actually gets the oscillations going. Same thing with the brush. The oscillator or the resonant circuit here happens to be based on the dimensions, making it an antenna.
Yeah, because a quarter wavelength, I'm not sure if a shield would work on the wires because it's a quarter wavelength long. That probably wouldn't be a good plan.
Stop shielding things. Goodness God. Don't shield it. Don't let the RF out to begin with. If you don't let the RF out to begin with, you don't have to shield it. Shielding it is a painful process. It's expensive, and manufacturing will hate you and will throw rocks at your design if you tell them that, oh, you've got to shield this. No, don't let the RF out to begin with. And you do that really simply by looking at the characteristic impedance of every single transmission line that, people that don't understand transmission line think of it as just a wire. Okay, it's not a wire, it's a transmission line. Calculate its characteristic impedance, and if it's anywhere near 377 ohms of free space, redesign the physicality of your device so the characteristic impedance is low enough to keep the fields inside the transmission line. If you're passing 100 amp of RF because you're running off to a great big motor in an electric vehicle, well, then you need a much lower characteristic impedance transmission line. If you're running silicon carbide FETs and you want to feed it, you need a very low transmission line, which is why they go to so much trouble to be able to have the bus bars one on top of the other for the Wolfspeed FETs. It's all physics.
So you could have worked with the geometry of the two wires going to the motor to change the characteristic impedance of the transmission line, yeah? I mean, I know that probably would be the cheapest solution. What about a shunt capacitor at the motor? Would that have worked?
Say again, please.
And what about a shunt capacitor at the motor? Would that have worked?
Well, what's going to happen? You're changing the resonance structure. Is the capacitor at the motor going to work, or will the capacitance at the motor cause a different loop that'll have a different area, which will have a different emission?
Right, you'll probably end up with a higher Q, different frequency resonant, right? If you have a capacitor that's just contributing to a higher Q resonator tank.
The other issue you have is that 1.5 gigahertz, if you want it to be a capacitor, not an inductor, you're pretty much going to have to use a small surface mount part, which I'm not sure you could get on the leads.
Exactly.
Yeah, it'll be a little guy. It'll be a little guy for sure, right? Yeah, a lot of people don't realize that you got to have two different size capacitors in order to deal with different frequency ranges, even when you're trying to shunt an IC.
Well, because a capacitor, what we call a capacitor is actually a combination of capacitance, inductance, and equivalent series resistance. And what its impedance is depends on what's your frequency of operation.
So
At some point,
what
it
we're
becomes
getting to
resonant.
here is think about the capacitor and think about the distance between the brushes and the capacitor. That is a series resonant tank. You have the inductance of the wires. There's two of them, one going to one brush, the other one going to the other brush. You have the length of the capacitor, which is inductance. If that series tuned tank goes series resonant, you have a problem. You will simply move the emission to a different frequency and possibly in a different direction off of the device rather than fixing it. But you can't always use a resistor. In this case, you can't put a resistor in the DC line going to a motor because you mess up the DC characteristics. Okay, so that is one time that I actually use a ferrite. And I profess profusely that I hate ferrites. I don't use them unless I'm absolutely forced to use a ferrite. Resistors
Joanna?
are cheaper and they're more broadband.
Joanna,
Yes.
a question on your solution. I like it. What I'm understanding the solution is I see it that you've knocked out the patch antenna, the perfectly tuned 1.5 gigahertz PCB was acting as a patch antenna for that circuit. And then it's just basically it's two leads sticking in the air, but you greatly reduced the emission because there's no antenna. There's no patch antenna to really pump out that signal.
I cut the antenna in two and put a big resistor between the two halves. And so the resonant structure that was formed between the quarter wavelength length of the PCB and the quarter wavelength of the wire, I cut it in half. I cut the antenna in half and I put a big resistor between the two halves.
Right.
It couldn't radiate anymore because the current was substantially lower by orders of magnitude.
Yes. Because when I see the picture that you're showing right now, it looks to me like if I imagine the motor as a transmitter, and then there's leads going to the patch antenna. That's how you would do it if you wanted to transmit 1.5 gigahertz, and your ferrite blocks off the PCB from being a patch antenna.
Yes.
Nice
the
work.
ground structure of the printed circuit board was literally half of the antenna structure. And the antenna structure was resonant, would resonate at 1.5 gigahertz. That is at the speed of light. The current that's traveling from the motor to the far side of the printed circuit board turns around because it sees an open. It turns around and comes back to the motor. And at the motor, it sees a open. It turns around and goes back towards the PCB, and it's bouncing back and forth. And because of the physical length of that conductor, it's resonating.
Perfect. I'm surprised they hadn't noticed that was a problem before they. How did this problem sneak up on them? Had they just adjusted the PCB size, or was it a new model design or something, or what happened here?
No, I just put a couple of ferrites in it.
Yep.
Okay.
No, I understand.
I mean, hey, production was supposed to happen 2 months ago. Okay. We can't get this thing fixed. Okay.
Right.
Here's the new artwork. Build it, test it, ship it, get it out the door.
Yeah. So it was a new design. That's why they hadn't noticed the problem before they put it in production. Is that
right?
Got it. Good. Thanks.
That's a DC motor too, right? So the designers
Yes.
probably thought they were dealing with a DC circuit. Everything's DC, life is good, and then you have a 1.5 gigahertz problem, which is pretty ironic.
Yeah, it kind of rattled them a bit.
Good show.
Well, should we let everyone go home? Any more questions?
This is Akio, and I took several screenshots because I'm a chapter photographer. So I will distribute a screenshot to all speakers. Some of them didn't use camera, so if speaker can provide own photograph or something, please do that. And thank you.
Yes, thank you. I really enjoyed this. I appreciate everyone's time.